Now let us consider a geometric interpretation of complex numbers. For that aim, recall how we define the set of complex numbers. First of all, we considered this Cartesian product of the set of real numbers. So this was the set of all pairs of ordered pairs of real numbers. So A and B are real numbers. Then we introduced two operations called addition and multiplication between the elements of this set of pairs of real numbers. Then we examine the correspondence between these operations with the operations addition and multiplication in real numbers. So real numbers, addition and multiplication. So there was a nice correspondence between this and this set. So let's write this as r squared and plus and star. So they behave exactly in the same manner. So we redefine the set of real numbers as a subset of this r squared, where the second component is 0. Then we redefined this set as the set of complex numbers, and now the new set of real numbers is a subset of the complex number, and they are both fields. Okay. So a complex number, then if z is a complex number, then it can be expressed as something like this. And this I is the imaginary unit. So in terms of r squared, this I is something like 0 and 1. Okay, and these x and y, they are real numbers. So in the original notation, this point, this element is expressed as x and y. So we can plot this point in the two-dimensional real plane. So x and y. And if we have z here, so the x coordinate is x and y coordinate is y. So we can represent every complex number as a point in this plane. And this plane, where the x-axis represents the real part and the y-axis represents the imaginary part, is called the complex plane. Or it has another name called the Argand diagram. Now, if you look at this diagram, you find that this distance between the origin and this point, z, is given as square root of x squared plus y squared, according to the Pythagorean theorem. And we define this distance as the modulus of this complex number. So the modulus of complex number z is defined as square root of x squared plus y squared. Okay, so this is called modulus of z. Or we could say this is the absolute value of z. Okay, now if x is a real number, then what was the modulus of x? it was defined as this. It is equal to x if x is positive or 0, or it is negative x if x is negative. Either way, the modulus of x is positive or 0, or we could say non-negative. But the same thing can be defined in another way. So we could write the same thing as this: square root of x squared. So this is, of course, greater than or equal to 0. So we can see that this modulus of a complex number is an extension of the modulus of a real number. Okay. We cannot define the modulus of a complex number in this way because we cannot order complex numbers. Okay. In the case of real numbers, it is arranged for example, we can arrange all real numbers in one direction. But in the case of complex number, there are two dimensions. So for example, if we have this point and this point, another point here, so which one is greater? This is a nonsense question. No, we cannot determine which one is greater or which one is smaller. So we don't define the modulus of complex numbers in this way, but in this way. So which is, in a sense, an extension of the modulus of the real numbers. Next, we define complex conjugates. Conjugate. So let's say we have a complex number z, which is x plus yi, where x and y are real numbers. Then its complex conjugate is defined as this: z bar x minus iy. So we swap this sign from positive to negative. So that's the conjugate conjugate of z. And obviously, if we take the conjugate again, so z conjugate of this, so from z we get the conjugate z bar, and from z bar we get its conjugate z double bar. That is complex conjugate of this is, again, we swap the sign here, so negative sign becomes positive sign, which is the same as the original complex number. So the conjugate of a conjugate is the original complex number. And as you can see, if z is actually a real number, then its conjugate is the same real number. If z is a purely imaginary number, then its complex conjugate is negative of that purely imaginary number. Okay. And if you multiply z and its conjugate, then you have this: x plus iy and x minus iy. And if you calculate this, then you get x squared plus y squared, which is the square of the modulus of z. And of course, which is the same as the modulus of the complex conjugate of z. Okay. Now let us prove some properties of complex numbers and their conjugates. First, We have already seen that for all complex numbers, uh, conjugate of conjugate is equal to the original complex number. So you already know this. Now, if z1 and z2 are complex numbers, complex numbers, then the complex conjugate of their sum is the sum of complex conjugates. Okay, so let's prove this. Suppose z1 is represented as x1 plus iy1 and z2 is x2 plus iy2, where x, I, y, I are real numbers and I is either 1 or 2. Okay? Then their sum is this. So we add the real parts and we add the imaginary parts, y1 and y2. So let's take the complex conjugate of this. Then that becomes x1 plus x2 minus I y1 plus y2. Okay, but this is x1 minus I y1 plus x2 minus I y2, which are complex conjugates of these. Therefore, this is the sum of complex conjugates. Okay. Next, z conjugate is equal to z if and only if z is a real number. Okay, so this is if and only if. So to prove this, we have to prove both directions. So assuming this, the left-hand side, we prove the right-hand side. And assuming the right-hand side, we prove the left-hand side. Okay, so let's suppose, so first we prove this direction. Okay, so suppose z bar is equal to z. So let's say z if, so z is x plus iy, so and also suppose where x and y are real numbers. Okay, then z bar is x minus iy. So since z bar, by assumption, since z bar is equal to z, therefore we have x plus x minus iy is equal to x plus iy, right? So this x and this x cancel. So we have therefore the imaginary parts must be equal. So that means negative y is equal to positive y. So that means 2y is equal to 0. That is y is equal to 0. Therefore, whatever the value of x is, then z is equal to z bar is equal to x, which is a real number. So the proof of one direction is done. Then we prove the other direction. So suppose z is a real number. Then z can be expressed as x uh, plus I times 0, right? Because the imaginary part should be 0. So if that's the case, then z bar is equal to x minus I 0, which is just x, which is equal to z. So the proof is done. And next, let's see. If z bar is equal to negative z, then okay, z bar is equal to negative z if and only if z is purely imaginary. So this can be proved in a similar manner as the previous result. So I leave this as an exercise. So since this is if and only if, we have to prove both directions. Okay. And next, if z is a complex number, then z plus z bar is a real number, right? So this should be easy, I hope. So this is another exercise. And similarly, if z is a complex number, then z minus z bar is purely imaginary. Well, I think we need some explanation about purely imaginary. So, for example, is 0 purely imaginary? 0 is a real number, but I times 0 is 0, but still we consider this as purely imaginary. Okay, this is just a convention. Otherwise, this claim doesn't hold. Okay, and I think this is also easy. So this is another exercise. And next, if z1, z2 are complex numbers, then the complex conjugate of their product is the product of their complex conjugates. Okay, so let's see if let's say z1 is equal to x1 plus y1, and z2 is equal to x2 plus y2. And of course, we're assuming x1, y1, x2, y2, they're all real numbers. Okay, so assume this. Then z1 plus z2 is x1 plus y1 times x2 plus y2. And that is x1, x2, and minus y1, y2 plus I, and x1, y2 plus x2, which one should come first? Y1, x2. Okay, so there its complex conjugate is this. So just swap this positive sign to a negative sign. Okay, so this should be equal to the product of the conjugate complex conjugates of these two complex numbers. So we could rearrange this into this form, but I think it's easier if you just calculate the right hand side directly, then compare the results. So this is x1 minus iy1 times x2 minus iy2. And this result is x1, x2, and that's minus y1, y2. You should check this. Then minus x1, y2, and y1, x2. So they are the same. So therefore this claim holds. Okay. Next, if z1 and z2 are complex numbers, we have the modulus of their product is equal to the product of their moduli. Okay. I think the plural form of modulus is moduli. So I think this should be easy. You need to just calculate both sides and compare them. Okay. But here's another way to prove this. First consider z1, z2 squared. Okay. Now we know that the square of a modulus is this. So z1, z2 times z1, z2 conjugate. Okay. But we already know that the conjugate of a product is the product of conjugates, right? So the second factor becomes this z1, z2 times z1 bar times z2 bar. But we know that the complex numbers form a field, so the products here are commutative. So we can change the order of product, so it becomes z1 times z1 bar times z2 times z2 bar. But this part is the square of modulus of z1, and this part is the square of the modulus of z2. Okay, and we know that the modulus is always positive, so if we take the square root of the both sides, this and this, we have z1, z2 modulus is equal to z1 modulus times z2 modulus. So that's the result. The next result is called the triangle inequality, and I think it's less trivial. It's called the triangle inequality. Inequality. So that says the modulus of the sum of two complex numbers is less than or equal to the sum of moduli of the two complex numbers. So this is called triangle. So consider any triangle. Let's say something like this. And the length of these edges are, say, A, B, C. and and the length of one of the edges is always less than or equal to the sum of the remaining edges. So this is similar to this the original triangle inequality. But does this what does complex number have to do with triangle? So to understand this, consider the complex plane. And suppose we have two complex numbers, z1 and z2. Okay, so that's x1 and y1, and that's x2 and y2. Okay, if you add these two numbers, the result is this. So graphically, we draw a parallelogram. So this and this is parallel, and this is parallel. So the result is this. So here, this point will be z1 plus z2, whose coordinate is x1 plus x2 and y1 plus y2, right? So since the length of this is the same as this, the length of this is z2 modulus, and this length is z1 modulus, of course, and the length of this sum is the modulus of z1 and z2, right? So this is a triangle inequality, right? The sum of this and this is greater than or equal to this length. Okay, so let's prove this. So let's say, suppose alpha is a complex number. Then alpha minus alpha bar is purely imaginary. Okay, so that means alpha minus alpha bar squared is a negative or non-positive number, non-positive real number. So therefore this is less than or equal to 0. Okay. Then we have this equality. 4 times alpha bar is equal to 4 times the square of the modulus of alpha. Right, this square modulus is equal to alpha times alpha bar. So we add this to the both sides of this. So add this term to the left hand side and add this term to the right hand side. So that gives us alpha minus alpha bar squared plus 4 alpha bar less than or equal to 4 alpha modulus squared. Okay, and if you expand this and do some calculation, this the left hand side becomes alpha plus alpha bar squared, and the right hand side is just right hand side. Okay, so if we take the and also note that alpha plus alpha bar is a real number. Okay, so we can just take the square root of the both sides to have alpha plus alpha bar less than or equal to 2 alpha modulus. Okay, now let alpha equal to z1 times z2 bar. Okay, so just substitute this into alpha. Okay, so that is let's see, So z1, z2 bar, and plus z1 bar, z2, which is less than or equal to 2 z1, z2 bar modulus. But the modulus of a product is the product of two moduli times z2. And the modulus of a complex conjugate is the same as the modulus of the original complex number. So we can get rid of the bar here. So there's no bar conjugate here. So this is what we have here, and now we have this equality: z1, z1 bar plus z2, z2 bar, and this is equal to z1 modulus squared plus z2 modulus squared. So we add this equality to the both sides of this equation. Okay, so the left hand side becomes z1 z2 bar plus z1 z1 bar and z1 bar z2 plus z2 z2 bar, and the right hand side is z1 squared z2 squared plus well, plus 2 z1 z2. Well, 2 and z can be confusing. Okay, and the right hand side is clearly this: z1 plus z2 modulus, their modulus squared. And the left hand side is less trivial, but let's see. Okay, let's factorize this with factorize z1 out from here. That becomes z1 bar plus z2 bar, and from here factorize z2 out, so z2 and z1 bar plus z2 bar. Then these factors are the same, so we can factorize them, and we have z1 plus z2 times z1 bar plus z2 bar. But this is the sum of conjugate is the conjugate of the sum, so we can put this. But we have z1 plus z2 and multiplied by its conjugate, so this is equal to z1 plus z2 conjugate squared. So after all, we have z1 plus z2 conjugates modulus squared less than or equal to the square of the sum of moduli. So if we take the square root of both sides, we have z1 plus z2 less than or equal to z1 plus z2. Now, of course, these moduli are all positive, so we just take the positive root of this. So here's the result, and the proof is done. Next, we define the notion of argument. So that is simply put, it is the angle on this complex plane. Let's say this is one complex number. The argument of z is basically the angle between this x-axis with this angle, so axis and this line. So this theta, this angle is called the argument. But strictly speaking, this is not just one angle, but it's a set of angles, because this angle and this angle plus 2 pi gives you the same position in this plane. So uh, the first definition uh, of the of the argument is this. So we define the argument of a complex number with modulo 1. So we first define the argument only for these complex numbers. That is the complex numbers on the unit circle in this plane. So that is unit circle. So this is a circle with radius 1. Okay. So maybe I should write u instead of z. So this is a unit circle, and argument of this u is defined to be the set of angles theta plus 2 pi k, where k is an integer. Okay, so this theta is this angle. U is here. So this is the argument. And the principal argument, so this is argument. So argument is a set. And the principal argument uh, is an element of argument, uh, principal argument is the element of this set and within this range, negative pi, excluding negative pi but including positive pi. So the angle between this range, this interval, is called the principal argument, and uh, we write with capital A. So in this case, this is theta. Okay. Then we define the argument for general complex numbers. So argument of z. So in this case, this z may not be of the unit modulus. So what is this? So if z is not 0, then we can define z hat as z divided by the modulus of z. Okay, so if we define this, then this z hat has the modulus of 1, right? To see this, it's very easy. So modulus of z hat is z over z modulus. But that is just z modulus over z. And this is 1. So the argument of z is defined to be the argument of z hat, because the argument of z hat is already defined, and since the modulus of z hat is 1, which is defined before. And the same holds for the principal argument of a general complex number z. So arg z is defined to be arg z hat. Sorry, this is capital A. Okay, let's see some examples. Arg1. 1 is a complex number. That's 0. Because in the complex plane, 1 is here. So the angle between this segment and this x-axis is 0. 0 radian. And this is the principal argument. And the argument of 1 is the set. So 0 plus 2 pi and 0 minus 2 pi and 0 plus 4 pi and 0 minus 4 pi and so on. So basically it's the multiple of 2 pi's. That's the argument of 1. It's a set. And similarly, the principal argument of I, which is this. I is here. So the angle is pi half. And the argument of I is the set of pi over 2 plus minus 2 pi k, where k is an integer. So any integer. And so on. Okay, next we prove one interesting property of multiplication by a complex number with unit modulus. So that is, let's say if we have a complex number, any complex number, and another complex number such that its modulus is 1. Then, on the complex plane, if we have this z here, and if we have this u here, this length is 1, and the angle, the argument is theta. If we multiply z by u, then this multiplication represents a rotation of this z by theta. So this z is rotated by theta, and the length doesn't change. The modulus doesn't change. So multiplication by this unit complex number with unit length, it represents a rotation with this amount. So let's prove this. First of all, consider, suppose in this in the first case, z is 1. Okay, then 1 times u is just u. So in the complex plane, this 1 is rotated by theta. This is u. So at least for this particular complex number, multiplication by u represents a rotation by the argument of u. Okay. Then next, consider any complex number. And let's say in this case u is I. Okay. So let's say if z is a plus bi, then multiplication by I gives us minus b plus ai, right? So in this plane, if we have z a b. Just write a b here. A b. Then if we multiply by I, then the resulting complex number is minus b I. So this is a, this is b. So it will be something like this. So this is minus b, and this is a. So that's minus b a. Now consider the distance between this point and this point. So that is so the difference between these 2 points is minus. So this, let's say, this minus this is a minus minus b. So the distance is squared, and plus b minus a squared. Actually, this is distance squared. So that is a minus b squared. Wait a minute. A plus b squared and b minus a squared. And that is, if you calculate this, we have 2a squared plus 2b squared. Okay, so the distance here is square root of 2a squared plus 2b squared. Okay, and what's this distance? That's the modulus of the original complex number z. So that is z is square root of a squared plus b squared. And what's the distance here? This is the modulus of zi. Zi, which is the modulus of this. So it's the same as a squared plus b squared. So if you compare these 3 numbers, this and this and this, then we can see that, see this, let's see, z modulus squared plus zi modulus squared is, that's a squared plus b squared plus a squared plus b squared. That is 2a squared plus 2b squared. And the distance between these 2 points is the modulus of z minus zi, right? And that is 2a squared plus 2b squared. So this is equal to this. Therefore, we have this. Now, so if you look at this triangle, then it says, the result says, the sum of the square of this length and this length, square of this length, is equal to the square of this length. So this means, according to the Pythagorean theorem, this means this angle is the right angle. So it's 90 degrees, or half pi. Okay, so this means multiplying by I, the imaginary unit, rotates this complex number by the right angle. Okay. And by the way, as you have seen, these length are the same. So multiplication by I doesn't change the length of modulus, length of the complex numbers. Okay, then actually this holds for any pairs of complex numbers. Say, suppose Z and W are complex numbers. Then, and also U is a complex number with length 1, modulus 1. Then multiplication of ZW is U, ZW, and that is ZW. So this means multiplication by U does not change the modulus of the difference between two complex numbers. Okay, so this is actually what we are seeing here. Right? It's a difference between this point and origin, 0, 0, right? So this distance doesn't change by multiplication by a complex number with unit modulus. Okay, and next, now consider any complex number on the plane. Then consider three distances. That is z minus 1 and z minus 0 and z minus I. Okay, so this is a triple of distances between z and the 3 points 1, 0, I. So on the complex plane, if z is here, then this is 1 and this is I and this is the origin. So we are considering these three distances. Okay, so this is z. Now if we give so now we gave this point and calculated these three distances. Okay, now conversely, if we give these three numbers, three positive real numbers, then this point z is the only point it has these three numbers as these distances from these 3 points. Okay, no other points. Let's say this is A and this is B and this is C. Okay, so suppose we have A, B, C. So these numbers are positive numbers are given. No other points than this Z satisfies these distances from these 3 points. Okay, now let's multiply these three complex numbers by U. Okay, U is again a complex number with unit modulus. Then, as we have seen, u z minus u is z minus 1, because if you factorize u and the modulus of u is 1, so this equality holds. And similarly, u z minus 0, well, u times 0 is 0, so this is still z minus 0. Okay, and u z minus ui, it's still equal to z minus I. So if you multiply by a unit complex number, then we still have the same triple of distances from these 3 points. So there is somewhere, let's see, there's somewhere on this plane a point. So that's uz. Okay, that has the same distances from the origin and from I and from 1. Okay, so this distance is the same as this distance, and this distance is the same as this distance, and this distance is the same as this distance. So what is this point? And by the way, U is somewhere, let's see, suppose U is somewhere here. And we know that multiplication of 1 by U gives us the rotation by theta. So this point is rotated to somewhere here. Point is rotated to here, and multiplication of U with I rotates U by right angle. So this U is rotated by right angle. So this is mapped to here somewhere. And multiplication of 0 by any complex number doesn't change anything. Okay. So that is, and if you rotate this z by theta, you will have some point that still has the same distances as these three distances. From U, and from this point, rotated U by the right angle, and the same distance as the origin. So that must be this point. Okay, so UZ must be that point, which has the same three distances as the original triple distances. So this is kind of complicated, but this shows us that the multiplication by U rotates a complex number by the argument of U on the complex plane. Next, we move on to defining some trigonometric functions that are sine and cosine and maybe tangent. Okay, so here's the definition. Let's say U is a complex number with unit modulus. And theta, let theta be an angle, or an element from the argument of U. Okay, remember this argument is a set of angles defined by the angle between U and the x-axis, the real axis. Okay, then we define two functions, sine from real to real and cosine, and also real from real to real. By this, cosine theta is the real part of U, and sine theta is the imaginary part of U. So here's the definition. So this means this U, this given U, can be expressed as this. U is its real part, which is cosine, and I, and its imaginary part, sine theta. And this argument, theta is an argument of U. Okay. So, for example, if you consider sine pi half, that is 1, because if you look at the complex number and consider the unit circle, pi half corresponds to this. That is I, and the angle is pi half. And the sine is the imaginary part. So that is 1. And cosine pi half is the real part, which is 0. Okay. So in general, if we have any complex number on the unit circle, if the argument is theta, then this real component is cosine theta, and the imaginary part is sine theta. And this is a periodic function because argument is, as we have seen, it's a set of angles with a period of 2 pi. So theta and theta plus 2 pi gives the same values for sine theta and cosine theta. So, as we define here, theta is any element of this argument. So, sine, for example, sine theta is equal to sine theta plus 2 pi k, where k is any integer. And same for cosine. Okay. And also, you should notice that cosine negative theta is same as cosine theta. Why? Because if you consider this u and theta, then negative theta corresponds to this negative theta. But the real part doesn't change, right? So cosine theta is same as cosine negative theta. And similarly, for sine negative theta, then it is negative sine theta, because this is sine theta. And then this is negative sine, that is sine negative theta, which is the mirror image of sine theta with respect to this real axis. So that value should be negative sine theta. So this is equal. So that is, cosine is a symmetric function and sine is a antisymmetric function. Next, let us prove some formulas for involving sine and cosine. So here's proposition. And let alpha and beta be any real numbers. Then cosine alpha plus beta is equal to cosine alpha times cosine beta minus sine alpha times sine beta. So that's the first part, and the second part is sine alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. So these are famous formulas for cosine and sine. But if we use, actually, if you can remember this, then it's fine, but eventually you will forget. But no worry. If you understand how you derive this, how we defined sine and cosine, then it's very easy to prove this formula or derive this formula. Okay. So let's prove this. So let u equal to cosine alpha plus I sine alpha, and v equal to cosine beta plus I sine beta. And from the definition of cosine and sine, we can see that these u and v have the unit modulus, right? So that's u v modulus is equal to 1. Okay. And we have seen that multiplying by a complex number with unit modulus rotates another complex number. So if we multiply u by v, then we can say that this multiplication by v rotates this complex number u by the angle beta. Okay, and also since both u and v have the unit modulus, then this multiplication, uh, this product has the modulus of 1. So this is modulus u times modulus v, and that's 1. Okay, so that means if we rotate, let's say this is u alpha and this is beta, then let's see, so same length, unit length, and if we multiply u and v, then the resulting uv will have the angle alpha plus beta, because alpha and rotated by beta gives alpha plus beta as the argument, right? So at least principal argument of uv should be alpha plus beta. Okay, so that means uv has as its real part cosine alpha plus beta, and I sine alpha plus beta. Okay. On the other hand, u is this and v is this, so we just multiply both. So this is equal to cosine alpha plus sine I sine alpha times cosine beta plus I sine beta. And if you calculate this, so this times this, and this times this, and so on, you have cosine alpha, cosine beta, and minus, so this times this, I squared is replaced with -1, so we have sine alpha, sine beta as the real part. And the imaginary part is sine alpha cosine beta and cosine alpha and sine beta. So if you compare these two complex numbers, the real part corresponds to this real part, and this imaginary part corresponds to this imaginary part, so they must be equal. So therefore cosine alpha plus beta is equal to cosine alpha times cosine beta minus sine alpha times sine beta, and sine alpha plus beta is equal to sine alpha times cosine beta plus cosine alpha times sine beta. That proves this formula. Okay. And the next theorem is called de Moivre's law. Okay, that says for any real number theta and natural number n, we have this equality, cosine theta plus I sine theta to the power of n is equal to cosine n theta plus I sine n theta. Okay, let's intuitively, this cosine plus I sine theta is a complex number with unit modulus. So multiplying by itself n times means we rotate the same complex number by theta n times. So that is equal to, that is the same operation as rotating the same complex number by n theta. Okay? So that's the meaning of de Moivre's law. Okay, but yeah, I mean, that's actually, that could be a proof. But just for the sake of formality, we prove this by mathematical induction, because this involves this natural number n, and we want to prove that this holds for any natural number. Okay, so uh, case if n is equal to 1, then this equality is trivial. Then, if n is 1, just cosine theta plus I sine theta is equal to cosine theta is plus I sine theta, so it's trivial. Now, suppose the claim, let's say this is star, this equality holds for n equal to k. Then this means cosine theta plus I sine theta to the power of k is equal to cosine k theta plus I sine k theta. Okay, so we can take this equality for granted by assumption. Okay, then cosine theta plus I sine theta k plus 1. So what is this? So that is cosine theta plus I sine theta to the power of k times cosine theta plus I sine theta. Okay, but for this part, we can use this assumption. We can replace uh, this. So this is equal to cosine k theta plus I sine k theta times cosine theta plus I sine theta. Okay, and then we expand this. Okay, so this times this times this, and so on. Then we should get cosine k theta times cosine theta, and imaginary times imaginary should be cosine k theta times sine theta. Okay, so this is the real part, and the imaginary part is sine k theta times cosine theta, and cosine k theta times sine theta. Now we can use the formula we have just proved. So this is equal to this should be equal sine. Okay, this should be equal to cosine k theta plus theta. So that is cosine k plus 1 theta. And so that's the real part. And the imaginary part is sine cos sin. So that's sine k plus 1 theta. Okay? So therefore, this is equal to this. So this equality holds for k plus 1. Okay, so that's the end of the proof. So we have proved this for k plus 1. So this equation holds for any natural numbers. Next, let us define the polar form of a complex number. Okay, so let z be any complex number that is not 0. Okay, and let r be the modulus of this complex number, and theta be an element of its argument. Then the polar form of z is this. Z is equal to the polar form of z is this, cosine theta plus I sine theta. So this r is the modulus, and this theta is the argument. Okay, it is easier to understand in terms of the complex plane. So suppose this is z, then the modulus is r. Okay, so that is this length is r, and this angle is is the uh, is the argument of z. So this okay. So this real part is r times cosine theta, and this imaginary part is r times sine theta. So instead of expressing this z in terms of real part and imaginary part directly, we can express in terms of its modulus and the argument. So that's the polar expression. Of course, this part has the modulus of 1. It's a unit complex number, and this is a positive real number. Okay. Maybe we could use some examples. So any non-zero complex number can be expressed in terms of the polar form. So suppose z is expressed as this. So that means its modulus is r and its argument is alpha. And another complex number as, let's say, s and cosine beta plus I sine Then if you uh, calculate their product, it becomes so RS, and you already know this times this gives us cosine alpha plus beta and I sine alpha plus beta. So what does it mean? Multiplication, let's consider this in this way. So z is multiplied by w, and that effect of multiplication by w changes z in this way. So it is magnified by s. That's the magnitude of the modulus of w, and it rotates z by beta. That is the argument of beta. So if we multiply z by w, then let's say this is w, then the result is something like this. So the length is magnified by this amount, by this factor. So this is r. So this length becomes uh, r times s, and the angle becomes this angle was alpha, this angle was beta, and this the resulting angle becomes alpha plus beta. So multiplication by a complex number magnifies, or in case this magnitude is modulus is less than 1, it will shrink the original complex number. But so magnification or shrinkage accompanied with rotation. So that's the effect of multiplication by a complex number. And also think about this, 1 over z. Okay? So that will give us 1 over r and cosine minus alpha plus I sine minus alpha. And we have seen that cosine minus alpha is same as cosine alpha. And sine minus alpha is same as minus sine alpha. Sine minus alpha is same as minus sine alpha. Okay. So how do we get this? Okay. Let's see. So this 1 over z, if we multiply both numerator and denominator by its z bar, we have this, right? The denominator here becomes modulus squared of z. Okay, but z bar is r cosine alpha minus I sine alpha, and the modulus of z is r, so it's squared. So we have this. So if we cancel 1r from a numerator and denominator, we get this result. Okay. And so if we combine this with another complex number, so z over w, you should be able to prove this. So this becomes r over s, and cosine alpha minus beta plus I sine alpha minus beta. Okay. Let us give a few more new definitions. So we've already mentioned that sine and cosine are periodic functions. But here's the formal definition of periodic functions. Okay, so let's say f is a function from R to X. X is a set. It can be any set. Okay, we say f is periodic. So if there is some positive real number, okay, so we're assuming this p is real, such that f of x plus p is equal to f of x. For all, there exists some p such that for all x, f of x plus p is equal to f of x. So in this case, the period is p. So p is the period, or a period maybe. Not the period, but a period of f. Okay, and there can be multiple periods. For example, in the case of cosine, 2 pi is a period, and 4 pi is also a period. So there can be many periods actually. So among all periods, the smallest period is called the fundamental period. So the smallest such p is called the fundamental period. Okay, so here's the definition. And so, as we already know, cosine and sine have the fundamental period of 2 pi. Okay, and another example. Maybe you already know that tangent x is defined as the ratio between sine x and cosine x. Okay, but this cannot be a function from real numbers to real numbers, because cosine x can be 0. And for example, in case where x is pi half, for example, cosine pi half is 0, but sine pi half is 1. So in that case, the result is not a real number. So we say tangent x explodes, or it has a singularity at x equal to pi half. So in order to make tangent x a function, we just we have two options. Okay, the first, we add something called plus minus infinity. So the codomain includes these two things. So they are not numbers; they are not real numbers for sure. So if we include this to express explosions, either to the positive side or negative side, tangent x is a function from real numbers to the union of real numbers with plus minus infinity. Or we simply exclude from the domain where cosine x becomes 0. Okay, so exclude, let's say, so tangent x is r minus x, where x cosine x is 0 to real numbers. Okay, so we have two options. Either case, this tangent x is also a periodic function, and you should plot the graph of this function. And it has the fundamental period of pi. And yet another definition is about even and odd functions. Uh, Previously I said symmetric and antisymmetric, but even and odd should be more appropriate. Okay, so here's the definition. Let f be a function from real numbers to real numbers. Then f is even means f of x is equal to f of negative x. So changing the sign of the argument doesn't change the value of the function. And f is odd, then it means maybe I should write f of negative x is equal to negative f of x. Okay. So an example of an even function is cosine, right? And an example of odd function is sine function. Okay, next we would like to define this famous constant E, which is also known as Euler's number or Napier's constant. And this constant plays an important role in the study of complex numbers. But first, let us define the natural logarithm. Okay, definition of natural logarithm. By the way, in this part of this lecture, we assume that you already know some calculus, like integration and differentiation and so on. Okay, so here's the definition of the natural logarithm. It's a function called log from this interval from 0 to infinity, not including both ends, to real numbers. And we define this function log as this. Log of x is equal to the integral from 1 to x, and 1 over t and dt. Okay, so if we plot this function 1 over t, it looks like this. So t and 1 over t is something like this. So it's a decreasing function. So when t is 1, this value is 1. Okay. And this integral means the area under the curve. So suppose this is x. So in this case, the value of log x is this area. Okay. But this x can be less than 1. You know, the domain of this function is from 0 to infinity. So this x can be less than 1. In that case, if this is x, then the area under the curve is negated, because if x is less than 1, so that is the upper limit is less than the lower limit of this integral. So the sign is inverted, and it's the negative of this area. Okay. And if x is exactly at 1, the value of log x is 0 because it's just this line. Okay, so here are some properties of this function. First, log of 1 is 0, as we have mentioned, because this is an integral. So if this lower limit and bound and the upper bound is the same value, then this integral is 0. So this holds. And second, this function is a strictly increasing function because 1 over t is always positive. So if you integrate this, this integral only increases as x increases. So increasing function, okay, let's say log x is strictly increasing. So this means if x1 is less than x2, then that means log of x1 is less than or log of x2. Okay, we say strictly. This means if x is less than x2, x1 is less than x2, then this log of x1 cannot be equal to the log of x2. Okay, it is strictly less than this. Okay, so this means strictly increasing. And also, the third property, this is continuous. So we haven't defined what continuous function means yet, but I hope you already know what it means, at least intuitively. Okay, so this means, okay, if you plot log x, it looks like this. It is strictly increasing and it takes value of 0 at 1. And when x is less than 1, it has negative value. Okay? And it is continuous function. So this means there is no gap anywhere. So it doesn't look like something like this. There's no jump. It doesn't happen. It's continuous. Okay. So those are the basic features of this natural logarithm. Okay, next we prove a little lemma about this function. Let's say y1 and y2 are real numbers and both of them are positive. Okay, then we have this equality. y1 times y2, its logarithm is equal to the sum of their logarithms. Okay, let's prove this. So by the definition of log, this is an integral. Okay, so that's 1 over x dx. Okay, previously we wrote 1 over t and dt, but this variable of integration doesn't matter. It's just a name. And by a property of integral, this is equal to, let's say this is y1 and x dx plus from y1 to y1 times y2 and dx. Okay, but this part is log y1. And the second integral, let's see, if we change the variable from x to, okay, just a moment, so let's change the variable from x to v, where v is defined by x over y1. then the second integral should be equal to from 1 to y2 and 1 over v and dv. To see this, oh, let's see. So dv is dx over y1, and 1 over x is let's see, y1 times 1 over y1v, right? From this we get this and this. So if we substitute this into here and dx, uh, so the dx is equal to y1 times dv. So this y1 will cancel. So this dx is substituted here. We get this. Okay. Okay. So when x is y1, then v is 1. So x is y1, then y1 over y1 is 1. And when x is y1 times y2, then v is y2, right? So therefore we get this integral. But this is just log y2. So we have proved this lemma. And as a corollary to this lemma, we can prove this handy theorem. So for all x between 0 and infinity and any natural number, we have log x to the power of n is equal to n times log of x. Okay, and this should be easy to prove because x to the power of n is x to the power of n minus 1 times x. So that is, using the lemma, we have this x times x, which is equal to log x n plus log of x. And then we can decompose this part in the same way. So in the end, there will be n log x's. So that should be equal to log of x. And if you want to be more formal, then you can prove this by using mathematical induction. And I suggest you do it. Now, if we apply this corollary to the case where x is equal to 2, we have this result. So log of 2 to the power of m is equal to m log 2. Okay, and we know that log of 1 is equal to 0, and log of x is strictly increasing. So this means log of 2 is positive. Okay, and if we increase the value of m, then this value can be arbitrarily large, positive value. And here's another corollary. For any x positive number, we have log of 1 over x equal to negative log of x. To see this, this can be proved very easily. So we know that log 1 is equal to 0. But 1 is equal to 1 over x times x. So we have 0 equal to log 1, which is equal to log 1 over x times x, which is log of 1 over x plus log of x. Therefore, we have log of 1 over x equal to negative log of x. So this means if x is greater than 1, then 1 over x is less than 1. So, so this means log of x can be, in this case, okay, wait a minute. In this case, log of 1 over x is negative. Okay, because log of 1 is 0, and 1 over x is less than 1 in this case. And log of x is strictly increasing, so therefore this must be negative. Okay, and we know that as x increases to infinity, positive infinity, then log of x can be arbitrarily large. So it can be very large. So this means log of 1 over x can be very large negative values. So it can be arbitrarily large negative values. Okay, so this means the values of log of x can span entire real numbers from negative infinity to positive infinity, of course excluding positive negative infinities. So let us summarize the properties of log function we have proven so far. So log is a function from this interval to real numbers. Okay, it's from 0 to infinity to real numbers. So first of all, it is strictly increasing. So this means log, this function is an injection. Okay, it's an injective. Okay, if two values at x1 and x2 are different, then log of x1 and log of x2 are different. Now this is a consequence of strictly increasing function. Okay, and second, it can take all real values. It can take arbitrarily large positive numbers and arbitrarily large negative numbers. So that means this function is surjective. And injective and surjective means it is a bijection. Okay, so this is a bijection. So log of x being a bijective function, then there exists its inverse function. Okay, so if log of x is a bijection, then we can find its inverse function. So here's the definition of its inverse function. So we define this exp, exponential function. We define this function from real numbers to positive real numbers as the inverse function of log. Okay, so this this is how we define this exponential function. Well, this turns out to be exponential function, but here we say exp. Okay, now we can define the value of e. So the value of e is defined as the value of this function with argument of 1. Okay. Okay, so let's see some properties of this function. So if x1 is equal to log y1 and x2 is equal to log y2, then we have seen that log of y1 times y2 is equal to uh, log of y1 plus log of y2, which is equal to x1 plus x2 by these definitions. Okay, so if we take the inverse of these, then we have y1, y2 is equal to exp of x1 plus x2. But we can also take the inverse of these, right? So that means this is equal to y1 is equal to exp of x1 and y2 is equal to exp of x2. So these things are equal. So exponential of x1 plus x2 is the product of exponential x1 and exponential x2. And this holds for all x1, x2 in real numbers. Okay. And now it should be easy to see that for any natural numbers, we have exp n equal to exp 1 to the power of n, which is equal to e to the power of n. Okay. And similarly, we have exp of negative n times exp of positive n. And we have seen that this is equal to this, minus n plus n, which is exponential of 0. But this should be equal to 1. Because as we have seen, log of 1 is 0. So by taking the inverse of this, we can see that exponential of 0 is equal to 1. Right? So this proves that from here, this is equal to 1. So exponential of negative integer is equal to e to the power of power of negative n. Right? Because, okay, maybe I should prove this a little bit more carefully. So this should be equal to exponential of n, but this is equal to e to the power of n, but this is equal to e to the power of negative n. Okay. So from this, we can see that for any integer, let's say z, maybe I should write I for integer. Okay, for any integer I is confusing. Okay, it sounds like imaginary unit. So let's say k, which is any integer. We have e to the power of k is equal to exponential function of k. Okay. And furthermore, this exp 1 over n is real and it's a positive number. And if we take the power of this, then this is equal to exp n over n, which is 1, which is e. So that means this exp of 1 over n is the unique real nth root of e, right? Because if we take the power of this to the power of n, we get e. So this is the root, the real root. Okay, and next, any rational number, okay, m over n. So this is a rational number, okay. M and n are integers and n is not 0. Okay, then exp of m over n is equal to this, as we have seen, this to the power of m. But this inside is equal to e to the power of 1 over n. This is m, but this is equal to e to the power of m over n. So we have exp of x is equal to e to the power of x if x is either natural number or integer or a rational number. Okay, so this is indeed an exponential function of x as long as x is a rational number. Okay, but we want to extend this to real numbers. So we want to say that instead of rational numbers, we want to say x is any real number. Okay, how can we do this? So that can be done by considering the fact that this function exp of x is continuous. Yeah, we've seen this is continuous. And any real number can be approximated by rational numbers to any degree of precision. Okay, so from this, we conclude that this function, the inverse function of logarithm, is indeed the exponential function with the base of e. Okay. Now, we prove another lemma. That is this. This is one of the most conspicuous properties of this function, exponential function. Ex is equal to e to the power of x. Okay. So this means this function, e to the power of x, or exp of x, is the solution of this differential equation. Okay, so let's prove this. First of all, let y equal to exp of x. Then, by taking the inverse of this function, we have x equal to log of y. So let's differentiate both sides with respect to x. So the left hand side becomes 1 and the right hand side becomes, by definition this is this integral of y 1 over t and dt. So this is the primitive function is 1 over y, and by the chain rule dy dx. Okay, so from this we have dy over dx is equal to y. So that is d dx expx is equal to expx, and we are done. Okay, at this point let us review what we have done so far. First of all, we defined this natural logarithm function, and we have seen that this is a bijection. So based on this fact, we defined this its inverse function. So inverse. Okay, then based on this function, we define this constant e as the value of exp1. Okay, then next we have shown that for any natural numbers, we have exp of n is equal to e to the power of n. Okay, then we extended this to any integers. So not natural number, integers. So for any integers, this exp of k is equal to the to e to the power of k. Okay, so we first show this relation for natural numbers, then extend it to integers, then we extend it to rational numbers. Then by using the continuity of this function, actually it comes from the continuity of the logarithmic function, then we finally obtained this relation for any real numbers. So this function, inverse function of logarithm, is indeed an exponential function. Okay. The next step is to extend this function to complex domain. Okay, so let's see. Okay, here's a definition. Let z be a complex number u plus I theta, where u and theta are real numbers. So we define e to the power of z as this exponential of u times cosine theta plus I sine theta. Okay, here we are defining this function, this z is a complex number. Okay, but this one is already defined because this u is a real number. Okay, so this is already defined, and cosine theta and sine theta we have already defined. So here we are defining a new function, exponential function with this constant e. Okay, e to the power of z, where z is a complex number. This means this. Okay, so here's the definition of a new function in complex domain. So this is a function from complex numbers to complex numbers. Okay. But you should be a little bit worried because is this function really consistent with the function we have defined for real domain? We could define anything, but if it's not consistent with our previous definitions, then we are in trouble. So to see this, any complex number can be a real number if its imaginary part is zero, right? So suppose its imaginary part is zero. So if theta is zero, then z is equal to u, which is a real number. So in this case, e to the power of z, the left-hand side is equal to e to the power of u times cosine 0 plus I sine 0. But sine 0 is 0, so it's gone, and cosine 0 is 1. So therefore, this is equal to e to the power of u. So this is the same as the exponential function in the real domain. So this exponential function is defined on the entire complex plane, so real z and imaginary z. But as long as this real axis is concerned, on this axis, this function is the same as the exponential function we have defined for the real domain. And by the way, if if theta is pi, then what happens? So that means we have exponential of z is equal to theta is pi, and let's say u is 0. In this case, we have exponential of 0 and cosine pi plus I sine pi. But sine pi is 0 and cosine pi is negative 1, and this is 1, and z is, in this case, z is just I pi. Right, so it's exponential of e to the power of I pi is equal to negative 1. So this is a very famous equation. Now let us prove further properties of exponential function in the complex domain. So here's a proposition. Let's say z1 and z2 are complex numbers, and k is an integer. Then we have e to the power of z1, e to the power of z2 is equal to e to the power of z1 plus z2. So that's one. And second, e to the power of z1 to the power of k is equal to e to the power of k z1. So these properties are exactly the same properties as we had for the exponential functions for the real domain. Okay, and proving this is not so difficult. We just go back to the definitions. Okay, so let's write z1 as u1 plus I theta 1 and z2 as u2 plus I theta 2. And of course u1, theta 1, u2, theta 2, they are all real numbers. Okay, then we calculate this left-hand side. So that is, by definition, e to the power of z1 is e to the power of u1, which is a real function, times cosine theta 1 plus I sine theta 1, and times e to the power of u2 cosine theta 2 plus I sine theta 2. So just expand all this, and in the end we have e to the power of u1 plus u2 and times cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And what is this then? So this is actually the according to the definition of the exponential function, this is the polar form of this exponential of z1 plus z2, right? So if we add z1 and z2, we have as the real part, it will be u1 plus u2, so that is this part. And as the imaginary part, we have theta 1 plus theta 2, so that is this. So in the end, we have this. And I leave the second part as an exercise. Okay, now let's go back to the polar form again. So first of all, we have this. So if theta is a real number, exponential of I theta should be cosine theta plus I sine theta, by definition of this exponential function in the complex domain. Okay, so if we have a complex number, any complex number with the polar form of this r times cosine theta plus I sine theta, then this is same as r times exponential of I theta. Okay, so this is another way to express the polar form. And of course, we have, if we take the reciprocal of this I theta to the power of -1, that is r to the power of -1 times exponential of minus I theta. Okay, so this is just like exponential function. Okay, and okay, we have also, if we have two polar expressions, polar forms, I theta times s e to the power of I psi. Okay, this is psi. By the way, this is a Greek letter, psi. And this should be equal to rs times e to the power of I theta plus psi. And also, if we take division, not division, ratio, I psi, then that is rs this and exponential I theta minus psi. Okay, and also we can express e to the power of I theta as cosine theta plus I sine theta, and also exponential of negative I theta as cosine theta minus I sine theta. So from these two equations, we can derive that cosine theta can be expressed as exponential of I theta plus exponential of minus I theta over 2, and sine theta as e I theta minus e minus I theta over 2I. Okay, so here are another way to express cosine theta and sine theta. We could have defined these two functions, cosine and sine, in this way if we already had defined the exponential function. Okay, that's all for today.